So today's a fun and very important topic for us, lecture for us. We're gonna talk about lists. We're gonna talk about two kinds of lists today, and we're going to spend some time comparing and contrasting them. One of them you've been working on the last couple of homework problems. The next one you'll get some practice to work on next week, starting Monday and Tuesday. So, as a review, one of the reasons that we're talking about this is that we're into a phase of the class where we're talking about algorithm analysis. And we're going to apply these types of principles to things that feel a little bit more like algorithms. But this is a good starting point because what we're doing is we're actually building a couple of different types of data structures. Well, actually, we're building the same kind of data structure. We're gonna implement it in a couple different ways. So this brings together a lot of the things that we've been talking about. It brings together the idea of abstraction behind an interface, that we can have two different classes implementing the same interface in ways that are very different. It also gives us some practice at looking at how these implementations affect performance for different types of operations on this data structure. So I don't know how I got to this slide. I'm struggling today. Okay, here we go. You know, and again, normally what we want to do and what we're going to do when we talk about lists is we want to talk about what happens when things get really big. And the nice thing about lists is that this is a very tangible property of a list. What happens when it gets really long, right? And what we'll see is that depending on the kind of list that you use, different operations are either fast or they slow down more and more as the list gets larger and larger. Okay. And the terminology that we use to talk about this is what's referred to as big O notation. And what we do in this class is sort of baby big O notation. We're not gonna get, you know, too formal about it. You're not gonna see too many equations on the slides, but we do want to be able to talk about general performance of a particular algorithm or particular operations on a data structure. We wanna be able to say, which one of these curves is this operation going to follow? Because obviously it makes a huge difference, right? When we see the difference between, you know, ON, which is down there kind of doing nice, hugging the axis, and ON squared, or O2 to the n, which are taking off like rocket ships and really causing things to slow down as the problem gets large. Again, I just want to remind you of something, and this is always important. I've run into this a couple of times myself recently, which is that a lot of times when we test our code, or when we're experimenting with things, we're down here in the shallow end, at which point a lot of different algorithms actually perform pretty similarly. It's hard to tell the difference between, you know, an n factorial algorithm and an n squared algorithm when you're using really small inputs. And this is one of the things that distinguishes you as a computer scientist, is that you might experiment with things over here in the shallow end, but you're gonna know that once things start to get big, certain things are gonna get bad quickly. Because sort of over here is where we're testing stuff, and over here is where good things are happening, success. Lots of people are using your app, lots of people are coming to your website, lots of people are using your new product, and then the differences between different approaches and different algorithms for solving problems start to become very apparent, right? Okay. So the data structure that we're starting to talk about, that you guys have been implementing over the last couple of homework problems and will continue to implement next week in a different way, is something that's called a list. So a list is a generalization of an array. Remember, a long time ago when we talked about arrays as a data structure, we said, what kind of structure does an array bring to data? Every data structure takes data and brings structure to it, as the name implies. With an array, it's easy to forget this, but an array associates a new piece of information with every item in it, which is an index. And arrays put things in order. So an array takes a series of items. They could be primitive types, they could be object references, and it puts them into an order. So it puts one in front of the other. That's the structure that we're bringing to the data. A list is like this. A list is an ordered data structure. We're gonna talk about some unordered data structures in the future. A list is an ordered data structure, meaning that it does that same thing. It puts items in order. When you add something to it, you have to tell the list where it goes. The difference with an array is that I can still get and set values, just like an array, but I can also change the size of it at runtime. and I can add things to the middle of it. So I can insert a value into the middle of the array, into the middle of the list, which causes the values behind it to shift over a little bit, and I can actually remove things from it. So I can take an element out of the list, which causes the elements around it to shift back. Lists are an incredibly common data structure. I refer to them as one of the two data structures that you meet in heaven. They are super useful. Every modern programming language has them. Normally, you just use them. You don't think about how they're actually implemented. So if you program in Python, you're taking 196, you've probably been using lists. And they have all these nice properties. You're probably telling yourself, this is so annoying about Java. I have these arrays that have all these limitations. Well, we're going to start to remove them, but we're also going to show you what's going on behind the scenes. We're going to show you some of what has to be done to give you some of these nice properties. JavaScript has lists, Go has lists. Pretty much every modern data structure just provides this data structure, every modern programming language provides this data structure for you out of the box. And you can just use it, which is incredibly useful. And again, these are really, really important to solving real-world problems. Lists and maps, which we're going to talk about in a few weeks or maybe a month. Armed with these two data structures, you can really sort of conquer the world. There's not a lot that you need at that point. There are some things that are required for more specialized purposes, but you can get a lot of work done with those two data structures. This is the first one. Okay. So, and what we're getting at today is that how we implement these, so we're going to be talking about two implementations of the same interface. These are two implementations that, from the perspective of someone using them, behave identically. They support the same operations. They have implemented the same interface. And so, in both cases, I can get and set items, almost like an array, but these are functions rather than, an array access. And I can also insert and remove things. So both of our implementations, the one that you guys have been working on in the homework and the one we're going to start talking about today, support all of these common operations, but they have very different characteristics. And this is something that we're going to start at when we're going to look at this first now when we talk about lists. When we talk about trees, what we're going to be doing is talking more about how different algorithms perform on trees versus lists. But then when we come back and talk about maps in a little bit, this will give us another chance to talk about different implementation strategies. This is a good, and so there's two, essentially the two types of lists we're talking about today present the following trade-off. So there is one kind of list, we'll come back and we'll summarize this kind of toward the end of the class on Monday, that gives you fast lookups and fast modifications of existing items. So I can get and set quickly, but if I want to insert or remove operations and actually change the items in the list, those operations are slow. And then there's another way to implement lists that gives me fast insertions and removals to particular spots in the list, and that's important. But lookups become very slow. So this is a really interesting trade-off here. There's nothing that gives me everything. There are approaches that try to blend these two to get some mixture of the characteristics, but there's a fundamental trade-off here. And so depending on what your application is doing, and we'll give you guys some questions on quizzes, and we'll talk about this in class a little bit, we'll say, okay, imagine that this is my algorithm. We're going to show you how it uses the list, and we're going to ask you to say which kind of list is better. Because depending on what I'm doing to the list, how I'm using the list, one of these two lists is usually faster, because the operation that I'm doing a lot is faster. If I do a lot of lookups on the list, but I don't change it very much, then I want to use a list that's backed by an array. If I add things to the two ends of the list very often and remove them very often, then I might want to use a list that's backed by a linked list. So we'll talk about both of these. And I also present different memory usage trade-offs. So there's several different levels here at which these lists are different, implemented differently, despite the fact that to you, as the user of this little list interface that we're going to implement, they are identical. All right, so list is an actual interface in Java. Here's the documentation for it. You can see that, as I've said, there are a variety of different classes that implement this interface. Some of them are abstract, some of them are things that you can actually use. And you can read the documentation for the list, and there's a variety of different items down here. Java's a mature language, and so there's a variety of different things, information about how lists are used and stuff like that. But here we start to see some operations that are gonna become familiar, that might already be familiar to us. Add, right? So for example, I wanna add an element at a particular index in the list. I have add, I have remove, I have get, I have set. But what we're gonna talk about in class, rather than trying to implement the Java list interface, which contains a variety of different methods that are sort of a pain to implement, like we could do it, but it would take a long time and you wouldn't learn a lot from it. So what we're gonna do is focus on the heavy hitters. These are what I consider to be the fundamental subset of operations that make something a list. So what do I have to be able to do? I have to be able to get and set items at a particular index. That's something that is a generalization of an array. So this is very similar to what I could do on an array, except that I'm calling a function now, rather than using the array index operator directly. And then I have these two additional operations down here, add and remove. So I should be able to insert, sometimes I call add, you could call add insert an item into an arbitrary place in the list, or remove an item from an arbitrary place in the list, from the front, from the back, and any point in the middle. And then finally, just a convenience method, which is useful for some of the types of operations that we're gonna perform on lists, a size method. Tell me how many items are in it. So again, arrays support get, set, and size. They don't natively support add or remove because those operations require changing the size of the data structure. And so this is the way that lists are a generalization of arrays. Okay. So you guys have made a lot of progress on this, on the homework. In fact, you're basically done with array lists. We've given you some of the code along the way. Today's homework problem contains a complete implementation of get, set, add, and remove for you guys to examine. These are from the solution set. But we'll come back and talk about this. So one of the things you might notice, so I have a constructor up here. I have get and set. Remember, one of the things we're starting to learn how to do is look at code and start to think about how long might this take to run. What do I see in get and set? Or maybe more importantly, what do I not see? Yeah. I don't see a loop. I see an array. I see looking up an element in an array. In Java, looking up an element in an array is, how long does that take? So it's important to know. This is one of our building blocks. Yeah. What's that? O of 1, it's constant time. If I have an array, plucking an item out of it or setting an item in it is constant time. So get and set, no loops, and a single constant time operation. These are constant time operations for this implementation of a list. Okay, good. Now let's start looking at some of these other guys here. This is where things start to get a little bit more interesting. So here's my remove method. I do some checking on the index to make sure it's valid. Before I get rid of it, I pull the item out that I'm going to return because the semantics of remove are that it returns the item that was removed at that index. Now what do I see? What's different from get and set here? I'm doing ON analysis. What's one of the things I notice in these functions that's going to make me wonder a little bit more about how long they might take? Someone who hasn't spoken up yet today. What do I see in remove? Yeah. I see a loop, exactly. So the answer was it depends on the length of the array. What depends on the length of the array? The loop that I see that starts here at line 43. What am I doing here? Essentially what I'm doing is I've created a new array that's smaller than the existing array by 1, because whenever I remove an element from an array, it gets smaller. Number of elements goes down. So I create my new array on line 41, and then what the loop is doing is it's copying items from the original array into my new array. And the only bit of subtlety here is this if statement on line 44. What that does is When it gets to the index that I don't want anymore, it skips it. So this code is important to look at and understand. This is definitely similar to things you guys will see on future quizzes. There are two indices that are being maintained here. There's an index into the original array. I've called that original index. There's also an index into the new array. I've called that new index. And in general, they're moving along in lockstep with each other. You see the for loop is incrementing new index, and then I'm incrementing original index at the bottom. So normally they move along together, except one spot, which is when I want to jump over the element that I'm getting rid of. And so there what I do is I just bump original index down one more spot, and I keep going. So that means that that one location that I want to elide or remove from the array that I'm filling gets ignored. Is there a question over here? Yeah, Jeremy. Yeah, there's multiple ways to do this. So the question is, do I need to maintain two indices? No. There's like probably 10 ways to write this loop. I can have one index, and I can just say, am I before the element that I'm removing or after the element that I'm removing? If I'm before the element I'm removing, I'm copying, you know, new index from the original array into the new array. If I'm after, I move one by one. Yeah. So, you know, you can do this in whatever way seems most intuitive to you. This is the way that seemed most intuitive to me. Okay, so again, you know, this is the reason, you might wonder, like, why don't Java arrays support this natively? This is the reason why, because it's non-trivial. I have to do some work here, right? I'm actually having to do an O(n) operation, depending on the size of the list. I'm going through and I have to do this copy. Add is similar in the sense, I mean, it's quite similar in many ways to remove. It does the same thing, except when it gets to the index where there's a new value, it uses the past value to fill that spot. Otherwise, it's copying things from the original array. But again, in both of these cases, when I look at add and remove, I see a loop. You know, this code up here we can ignore for the purposes of our O(n) analysis. It's really this loop right here and the similar loop in remove that are going to get bad when the array gets really big. It's fine when it's small, but once, you know, my list starts to have lots and lots and lots and lots of elements, this is going to slow down. Questions about this before we go on and talk about a different way to do it? So let's fill out this table. So for an array list, this is an implementation of the list interface that uses an array internally to store the values. What is the performance of get and set in big O notation? O1, right? What about add and remove? Yeah. So I'm talking about our implementation. Yeah. O(n), thank you. Right. So in general, there's work that I have to do inside add and remove. And the longer answer to that question points out what I'm about to talk about. So this is a fairly naive implementation of an array-backed list, in the sense that every time I make the list smaller or bigger by removing or adding elements, I copy the entire array. So what's a slightly more clever way to do that? Or to implement this? Yeah. Yeah, so the general solution to this problem is, so our implementation is always maintaining an array that is the exact right size. And that's nice because it only consumes the exact right amount of space in memory, but every time I have to add or remove, I've got work to do because I need an array that's slightly bigger or slightly smaller. Particularly when I have to add. I have to allocate a larger array. The solution to this is to essentially maintain an array that's bigger than I need. So if you create an array list with 5 items, it might go out and get an array that stores 64 items. Just have it ready. Because it's assuming, oh, you're going to add stuff later. So later when you add, when you go from 5 to 6, I don't have to allocate a new array. When you go from 6 to 7, I don't have to allocate a new array. When you go from 7 to 8, until you get to 64, and now what I might do is say, oh, the array's getting big now, I'm going to make it twice as big. So I go out and I get an array that's 128 items long. What this means is that, right, so when I need more space, don't make an array just one bit larger. Get a big chunk so that I don't have to actually reallocate an array for a while. And then when I'm adding or removing, we're not gonna show an implementation or talk about this. This is just a little bit of sort of fun Java internals. When I add or remove something, I'm just shifting items around. I don't have to allocate a new array. Now, I want to point out the fact that depending on where I'm putting the item, I still have to shift stuff around. So if I insert into the middle of the array, I still have to move all of the items that are past that insertion one slot farther down. And so insertions and removals, depending on how this is done, can still be roughly O n. Depends on where I'm putting it. If I'm adding to the end of the array and I have space, it can be O1, right? But if I'm removing from various points, I need to collapse the space around. So this can still be O n because I have some copying to do. But it's still going to be faster because this step right here, this line, when I'm actually allocating a new array, line 41, that takes time. That causes Java to have to go out and find some memory and stuff like that. And so this is something that will slow down a little bit. And so if I don't have to do that every time, I'm good. Right. So I just wanted to point this out. This is kind of a clever optimization. And this is a place where what we're really doing is we're trading off time and space. So I'm wasting memory. A little bit of memory, not a huge amount. I'm wasting memory in order to make certain operations faster. Is that a good idea on today's computers? To waste like 32 bytes of memory to make something a little faster? Always. Almost always. Today's computers have a lot of memory. It's almost always a good idea to waste some so that I can make my program go a little faster. Right? So this is why, this is how, I suspect this is what array lists do internally, the actual Java array list, not our simple one that we're using for the sake of the example. All right, questions about this before we venture farther forward? Yes? Mm-hmm. So the big savings is not having to allocate the array. And that's something that, we're not gonna get into very much, but whenever you allocate an object in Java, whenever you call new, Java has to go out and find memory for that, right? That takes time, right? And so not having to do that on every step will cause things to speed up. The copies I still have to do, right? But where I'm really winning is that I don't have to do that new array allocation during every add and remove. Does that make sense? Particularly during add. I never have to do it during remove, because remove I'm just sort of collapsing things down. But now a large number of the additions to the array don't actually allocate any memory. This is something you will learn much more about when you get to 241. You guys will actually write a memory allocator, and then you will see that there is some complexity to grabbing and releasing memory. Not something we're going to talk about here. So when we talk about this type of ON analysis on quizzes and stuff like that, we're asking you about runtime. And we will usually allow you to ignore the overhead of allocating any memory. But it is a real thing. Good question. Other questions? Okay, so there's another way to do this. There's another way to implement an array. This is something that's known as a linked list. This is our first new data structure in a while. So what is a linked list? A linked list is a way to store values in order, but instead of using a built-in Java array, what I do is I create a new class of object. In this case, I'm calling it an item. That item contains two things. Two things in the simple case. The first thing it contains is a value. In this case, I made it an object, so this can store any Java object. The second thing it contains is a reference. What is that reference to? So each instance of item contains an object called value. It also contains a reference. Reference to what type? To an item called next. So this is our first example of something that's actually a recursive data structure, or a recursive class. It contains a reference to itself, or to another instance of item. Normally, I'm not gonna contain a reference to myself, but I contain a reference to another item of that class. What this allows me to do is to link things together, as the name implies. So here's an example. I've created one item here. I'm using it to store an integer, and again, I'm casting it to the integer object wrapper type that we talked about for the 20 seconds that are required to talk about it last time. I'm setting the next reference on this new item to null. And I have a reference to it as items. So here's where this starts. How can I add another item to this ordered list? How about like this? So now what I've done is I'm rewriting the item reference that I had called items to refer to a new item, but when I initialize that new item, I'm setting its item reference next to the item I created previously. So now I've got two things in order. Let's do that again. I'm gonna do this one more time. So I am maintaining a reference called items. That reference refers to the first item in my list. That item has a reference to the next item in the list, called next. That item has a reference to the next item in the list, called next. And then that item is the end. And so its next reference is null. Questions about this before we go on? For many of you, this is new. One of the reasons I really like talking about lists is it's great practice talking about Java references. And so if you can wrap your head around this stuff, you really do understand how references work. Okay, well, what are we gonna do with this thing? So let's start building a new implementation of a list. I'm gonna call a simple linked list. Eventually, once we're done after a couple of homework problems and a little work today, we're gonna implement the same list interface that we've been talking about with array lists. And so we'll have a simple array list implementation that we've already completed. We'll also have a simple linked list implementation. We'll be able to talk about the trade-offs between the two of them. There's something new on this slide, though. Anybody notice it? It's one of the fun things I get to do is continue to challenge you with these new object-oriented programming concepts. Yeah, over here. Yeah, what's going on line 9? What on earth is this? It's a class inside another class. What is it doing there? Is this allowed? Yeah. This is called an inner class. So a brief, extra little bit of Java object-oriented goodness. In Java, I can define a class inside another class, just like this. So my class simple linked list defines a class internally. Doesn't have to be in a separate file. It can live right inside the class. That new class behaves, in many ways, identically to the classes that you're already used to using. I can provide methods for it, I can create constructors for it, it can have state, and it can have data, and implement algorithms. It's just another class. Except there are a couple of new things I can do. So there are several different types of Java inner classes. This is what's called a nested inner class, because it's nested inside an existing class. Remember when we talked about public and private and protected, we pointed out that Java classes, outer classes, the only kind that you've known about until this point, cannot be private. Inner classes can. So that's one of the things that's kind of interesting about them. I can define an inner class as part of my class, my outer class, and I can use that internally to maintain my own data structures, and that's what we're going to do with it when we implement our linked list. but I don't have to share it with anybody. No one else has to know about it. And what we'll see when we implement our linked list is that nobody knows about this inner class. People that use our linked list call get, set, add, and remove, just like it's any other kind of list. Internally, I'm using this to structure the data so that I can do various things to it, so I can implement those operations. But to the outside world, this class might as well not exist. The other thing that you should know about inner classes is that their methods have access to private variables in the outer class. So if my outer class here, simple linked list, had a variable that was private, and it might, methods defined on the inner class are allowed to access that variable. This is a little bit different than how Java encapsulation normally works. Okay, questions about this before we go on? This is not really that hard to wrap your head around. We're gonna see some examples of what to do with this. Yeah, was there a question here, or was it? I was thinking about this yesterday. I don't know. We should try it. So the question was, can a outer class access private methods from the inner class, or private variables from the inner class? I will try this and find out. It can certainly create the class, but the question is, does it have to use getters or setters to access those private variables? Or can it do that directly? I don't know. We'll try it on the forum, and we'll report back. Yeah, Jeremy. Well, not necessarily. So the question is, does each instance in the list contain a reference to the one that was created before it? In the example that we just did, it does. But in general, no. It contains a reference to the next item in the list. That item might have been created after it, might have been created before it. It doesn't matter. So it's a great question. So the way that a list imposes order, a linked list, is that each item in the list tells you two things. It tells you, here's my value, and here's where to find the next value. And so if I start at the beginning, I can locate a value, get to the next value. Locate that value, get to the next value. Eventually I get to an item in the list that has null because it's the last item in the list, right? So that's how lists order data. They tell you, here's the value. They also tell you, here's where to go to get the next value, if there is another value in the list. Okay. Right, and why are we using this here? We're using it really largely because there's no one else, like I said before, nobody else is gonna use item. It's only for my simple linked list class. I don't wanna share it with anyone else, and it's never going to be visible to anyone. What you'll see at the end of the day is when we're done with get and set and add and remove, those methods will return nothing or objects when they need to, and nobody who uses them will have any idea what's going on behind the scenes. This is kind of the point of things like interfaces. I can use it without worrying about how it's implemented. Okay, so let's get started with this. So this is essentially the beginnings of my simple linked list class. I have this inner class called item that I'm gonna use to store the values and maintain linkage between them, so I can find a value and I can find the next value. And then the one piece of information that my outer class has to maintain. Remember, the outer class, or the simple array list class had a whole array full of values. I don't need a whole array, I need one item. Because all I need to know is, where does the list start? All right? So, let's try doing add. So we're gonna do this together. And we're actually not gonna do add. We're gonna do a special case of add. So we're gonna write one of the cases for add, and then we'll come back and you guys will do some of these on the homework, or we'll do them in class later. Okay, so I'm gonna do public void add object. I think my index was first, right? Add index object to add. All right, so this is part of the interface. We're not gonna implement the interface yet because there's a bunch of methods on it we're not finished with, but we're gonna start. All right, we're gonna start with add, and we're gonna start with only one case in add, which is that if the add index is 0. So if the add index is 0, where is this new item going? At the start. So what do I need to do to add it to the start of the list? There are two things. So I'm being passed an object. What do I need to do here? Yeah. Exactly. So the first thing I need to do is when I create the new item, I need to make sure that the next item is the current start. So when I create my new item, and I'm just gonna put that in here for now. I don't know why I'm suddenly getting 4, okay. New item. And I need to pass it the object that I want to store in it and the current start, right? What happens if it's null? If start is null, what does that mean about this list? How many items does it have? 0, it's empty. So this is okay. It's okay not to provide a constructor for this yet because when I create one, it's empty by default. So that's fine. All right? But I have something else to do. So now I've created my new object, my new item, and I've linked it to whatever the previous start was, but I need to do something else. New is gonna pass me back a reference to this new item. What do I need to do with it? Eventually, I want to be able to find this again, right? This is now the item that's the first item in the list. So where do I store a reference to that? My linked list class has one piece of information it needs. It's part of the outer class. And that's the starting point for my list. That's it. When I add an item to the beginning of the list, do two things. I create the item, and I make sure that the item links to the rest of the list, if there was one. And then I save the reference as my starting point. That's all I have to do. All right, so let's see if this works. First of all, simple linked list. Simple linked list is equal to new simple linked list. I'm gonna do I'll do this. All right, so nothing exploded. How do I know whether or not this worked? Yeah, it's kind of hard to figure out. Let's do the following so we can have some sense of what's going on here. I'm gonna set this to public, just for the time being. Let's print out what's at the start right now. That's null. So when the list is initialized, my starting point is null. Now, after I add a value, let's print it off again. Okay, so now I have, and you can see this is an instance of item. It doesn't have a toString method yet. But let's just try calling the toString method on whatever is in there. And actually, let's call it on the value that's in there. Okay. So what happened here? I started off with an empty list. I called add. Add created a new item inside the if statement. And then it made sure it remembered where that item was because this is the new start of the list because I'm adding it at index 0. What is the print statement doing? This is a lot more dereferences than you guys are using to see. So I'm starting with my simple linked list. It has a public member called add that refers to an item. I'm dereferencing that item. That item has a member called value that is clearly not private because I'm able to access it here. That value is an object. And then I'm calling, sorry, I pushed the code I'm talking about a little bit too far down. And then I'm calling its toString method. So simple list gets me the list, start gets me an item, value gets me the object that's stored in that item, and toString converts it to a string. In this case, the object itself is an integer, and so I can call toString on it. Questions about this? I can't tell if you guys are just like happy it's Friday or stunned into submission or what. Yeah, back here. Yeah, I think that's true. So I don't think I have to call toString. That's a good point. Let's try that. When I call printf, normally I get toString by default, indeed. Other questions? Jeremy. Well, how many objects do I have in my linked list right now? 1. So what should the next value of this item be? Let's find out what it is. Yeah. So instead of printing off its value, let's print off its next pointer. It's null. Let's have some fun with this. Let's add another value. Maybe I got lucky and this only works once. Let's find out. Okay. So now I'm adding 2 values. Oop. So now let's do the following. Let's start with the list. Let's get the start. Let's get its next reference. Okay, so now the start has a next reference. What does that reference refer to? It's another item. So I can get its value. It's 10. So when I started off, I had an empty list. I added 1 item at the beginning. That item was 10. Then I added another item at the beginning. That item was 12. So the item that was at the beginning is now the first index. So if I print off the value of the first item, it's 12. Questions about this? We will do more with this. You guys will get more practice. Okay, so now this is what we've implemented so far is a special case. Here it's called add to front. An add where I'm inserting something at the beginning. What is the big O complexity of this operation on a linked list? Let's go back and look at it. Do I see any loops? Yeah, this is O1. That's pretty cool. Remember, my insertions into my array list were much more expensive in the general case. Here, any add to the front of the list, O1. All I do is create a new item, and then I change some references around. That's it. There's no loop. Pretty cool. However, obviously, there's a catch, right? So again, this is all about trade-offs. So what I've gained here is the ability to do really fast additions to the front of the list. And if I'm clever, I can do them to the back too. But what about get? Remember, there's 2 operations. So first of all, I'm not even halfway done implementing add. I've only implemented 1 special case of add. So I'm clearly not done with this interface. I have to do the general case of add, and then I have to do remove as well. But I also have get and set. And with my array list, get and set were really simple. Just a single lookup. What's different here? What do I have to do? Yeah. Yeah, so now I have to follow the list. So here's an example. Let's say that I've added several items to the front of my linked list, and here's what it looks like when I do a get. All I maintain is a reference to the start of the list. That's all I have. So now you say, get the second item, or get the third item. Get the item with index 2. What do I have to do that? I have to start at the front, and I have to ask it, what's your next value? And it says, there it is. And I ask it, what's your next value? And it says, here it is. Every time I'm doing this, I'm counting And finally, I've arrived at the correct value. So last time we talked, and this is a terrible analogy, but it's kind of fun, about, a row of seats being like an array. If I need a particular index, I can kind of go right to it. I can count, I can kind of measure the width, and I can find the exact spot. A linked list is more like if I gave all of you a piece of paper, or the way I constructed my list was I gave you a piece of paper that said the next student in the auditorium, and they had a value. So I'd have to start here. I would say, okay, you're the start of my list. Where's the next value? And you would say, okay, they're up in the balcony. So I have to go up there, and I have to ask them, where's the next value? And they say, oh, it's down over here. I have to keep doing this. So it's much, much more expensive on a linked list to get to the value that I'm looking for. And this is true. Now, you might notice something here, which is that this primitive of finding a spot in the list is used in get. It's used in set, because I have to find the value to change. Where else is it used? It's used in insert. It's used in add and remove, too. Because the general case of add and remove is I want to put something into some spot in the list. And so the first thing I have to do is find that spot. And so this property of linked lists is going to turn out to affect every single operation that I implement. Does that make sense? To implement add at an arbitrary index, I have to find that spot first, and then I'm going to do some work to do the add. Same thing with remove. I have to find the value to remove first, because you're telling me to remove it based on an index. So I have to find that value, and then I have to do some work to take it out of the list. Okay, I think I'm at a good stopping point, so we will come back and continue this. So here's the plan for Monday. We have a midterm next week. It's going to be awesome. You guys are going to have so much fun. It's going to be a fantastic, so format of the midterm, 3 programming questions, 20 points each. There will be partial credit on some of them. I know. Like, and by some, I might mean like 1. So just relax. Okay, 10 multiple choice questions. These are problems that I think you guys are well prepared to solve. There'll be a problem on implementing an object. There'll be a problem on implementing an interface. The other one I'm not sure about yet. Okay, on Monday what we're going to do is I'm going to finish talking about linked lists, which will probably take about 20 minutes. We'll have homework problems Monday and Tuesday on linked lists. MP4 is due on Monday. We're not releasing MP5 until Friday. So this is the same thing we did last time. There's no MP to work on during the midterm. There will be homework problems to do, because got to keep moving. Monday, we're going to finish linked lists, and then I will do general Q&A about objects, so you guys are ready for the midterm. I hope you guys have a fantastic weekend. Good luck finishing up MP4. I have office hours today at the usual time. I will see you on Monday.